Go ahead.
Yeah, so let me share my thing first. Yeah, so hey, I'm Prakyat. I go by PK. I did my work on robotics and continuous learning. Did my PhD in robotics and continuous learning. Currently, I am working in Flagship in Boston on biotech for machine learning for drug development. Um, yeah, so I can talk more about what I do a bit later or in Discord. And also, we have a lot of open positions. Reach out to me if you're an ML as a machine learning engineer or AI engineer. We'd love to hire you. So today I'll be presenting Hallucinations paper. This was a very interesting paper. Seems an under like uh, topic which has been brewing for a long time. Um, People have trying to ground models, like Gemini tried to ground models through its search. We always do citations and backtracking information through citations and ensuring that no hallucinations are surfaced to the users. But this is an interesting approach where the main focus is, can you detect hallucination while the model is generating? Let's say you're streaming responses, and as soon as you detect uh, model is not confident, can you just say not generate it or say, okay, I don't know. So they use some interesting approaches to do that. So I'll do a deep dive on what they changed, what model architecture they changed, and like some interesting results as well. So the TLDR is that the motivation is that, can you identify hallucinations while you're streaming? Um, the limitation of the current approaches is that one of the main state-of-the-art method is called a semantic entropy. The idea here is that you just sample it multiple times, and you see how many times it generated the same result, and you group them, and then make sure that okay, the cluster is small enough, then okay, maybe it's not a hallucination. It's not a foolproof way, of course. It fails all the time. Other hallucination methods are very time consuming and requires a lot of resources. Um, yeah, so the approach they did is they have something called as spans. They say it's a collection of tokens. And they use web search to identify, okay, if this span is true or not. I will go a bit deeper into like how they do this, etc. And they have a probe, linear probe, which they attach to the model in the finer layer or whatever layer you want. And then that essentially gives you the probability of this token is hallucinated or not. And they train this model next token prediction way, and they do some loss manipulation to ensure that the probability uh, is correct. And they achieved the state-of-the-art results for hallucination detection. And the context here is that I also tried to train this model, and it works pretty well. And also it generalizes pretty well. Um, so you can think of it as like instruction fine tuning for hallucination. So even though you don't use that many samples, but now you can use that probe to do hallucinations check for any topic that model is pre-trained on. So which is kind of awesome. Yeah, so that is a TLDR. So let's dive into the paper. Here, the main thing here is that they don't identify hallucination for the whole sentences. They identify hallucination on the token level, which is super powerful. Like I mentioned, super helpful for streaming. And yeah, so and another key contribution they mentioned is that they they use web search to first generate a data set for the hallucination. If you go back and think of how instruction fine tuning was done, you just get some text and you pass it through a language model to create in some question answer pairs. Here, the same way they ask LLM to generate some text. They use a web search to ground that. Ground and make sure okay, this text is, this token is wrong, etc. So that is the main contribution they mention. But I have some takes on this. I'll explain to why we can make this even better. We don't need web search. So yeah, I'll explain that a bit later. And then the other one is I found it interesting, is the linear probing approach. It's like um, attaching like a small linear probe at the final layer to identify the probability of this token is correct or wrong, is super powerful and can be used for other things as well. They have some different applications in the paper, which I will cover. Yeah, like I mentioned, state of the art results. Compared to like basic methods like perplexity, semantic entropy, etc., they were able to achieve everything. Yeah, so here is a very high level view of how their data looks like, how the labeling will look like. Here you have a response generated by 3.1 llama. We have some text here, and it essentially says that okay, this 29-year-old is 29 is wrong, and then it's able to identify what are the key components, entities they mentioned, and also identify which of these components are wrong, which of these components are right, etc. Very high level. Um, um, it's pretty strained in a very interesting way. Um, yeah. So and not so they're not predicting on every token, which is also super important. So every token doesn't have, like, for example, Rayleigh v. California. Here, Rayleigh v. California is not labeled as 0. Uh, uh, they essentially think of Rayleigh v. California here, the first 3 characters, as unimportant tokens, and then they have 573 US 337 the following tokens as important tokens. So you can think of it like they're doing 2-level classification. One is like, hey, the token is important, and the second one is it hallucinated in the same training run, right? So that is which is an interesting approach. I don't think anybody else has done that. Um, yeah, I'm going to skip over the introduction part of it. It's just they just mention that okay, nobody has done this. The current models are all like citation checking methods, etc. Okay, so yeah, the most of it here is yeah. So they mentioned that they use a frontier model to do web search and extract entities, which are either it can be true or it can be false. They use a Sonnet here for Sonnet 4 with web search to label to essentially extract. They give a sentence, and then the Sonnet does a web search and comes back with a JSON saying that okay, these characters are wrong, and they use that as a training data set. So my take here is that I've not tried this yet, but I want to. I will do that very soon. We don't need web search. My take here is that okay, we can just have data set, and then we can inject hallucinations. Let's take a wiki data set and change the names and dates, etc., and use that for training as well. I don't think doing web search adds anything. It's just API cost. So that is my take. Yeah, so, and also feel free to jump on and ask me any questions. Oh, I see a lot of questions in chat already. But the ground truth is generated. So can you explain what do you mean by that?
Yeah, sure. So my understanding of why they did it this way was that they took they took text and they generated whether or not the entities were based in fact or not, because the text itself was a large generated corpus. So so that you can get, I assume they generated 10x because they said they like expanded the long form or whatever it was called, that data set by 10x, and I presume they did that to get a larger training set.
Yeah, that makes sense. That makes sense. Don't you think the training set will be even more if you just do ingestion of hallucination rather than verification?
Yeah, I mean, that's valid. Yeah, I mean, you would still have to, yeah, I guess, sure. So you could just go and like, inject hallucinations. Yeah, no, I guess, I agree with you actually.
Yeah, and because maybe I'm jumping too ahead here, but in the results they mentioned that they used data generated by, let's say, JAMA, and then they used it in Llama, and they still got the same amount of performance. So even like they used Llama 3 8B data and 70B model, and they were able to get like actually better performance. So that, which means that, text, underlying text, what generated doesn't really matter, which is awesome. Yeah, so which was for verification of truth or falsehood of generation. You might want there is another question saying that I think the web search was for verifying the truth or falsehood of the generation. You might want to generate hallucinations. So true. There's a question saying that you might maybe too much out of distribution sampling. That is a valid point. If you inject hallucination, not too much out of distribution, um, that's a very valid point, and I didn't think about that. Um, yeah. So let me jump into the next part of the paper, which is related works. So I think the motivation here is from the Tegmark paper, where they use linear probes to identify what is the representation or like truth directions. They use that to do hallucination detection, which was super like just orthogonal thinking. Um, and then the other related work is an uncertainty like based detection. This is essentially like perplexity, right? So when the model is generating tokens, identifying like, hey, what is the perplexity of this token? That is another, they say it's a motivation for this work. And yeah, so, and the last one is external verification. This is what like most of the industry uses now. Like essentially, hey, generate citations for your text, and like, okay, for this sentence, the cite is from the cited text. Verify that is this sentence related to the cited text or not. Right. I'll come back. So this diagram is related to the data set they generated. I'll give a more explanation on this in the next section. But the idea here is that they started with a long fact data set, and then they added some more biography questions, legal prompts, more topic focused queries. These topics were biology, chemistry, etc. And they asked a language model like Llama. Once the language model generated the queries, they passed it to, like I mentioned, state-of-the-art LLM like Claude 4 with search to verify that on token level is this tokens correct or not. Yeah, so that is the data set generation process, and they also released the data set, which was super nice. And the code is also released. By the way, you can train this super easily. Um, Yeah. So yeah, like I mentioned, the data set is they took the long fact data set was already published and they expanded on that and then created this 25,000 questions data set. Yeah. And token level the token level annotation is there are three annotations that they let the Claude generate: supported, not supported, and insufficient information. So supported is labeled as let's say um, 0, and not supported and insufficient information is labeled as 1. So that is the thing and what they did. And they also did some human verification, if you say so, like the quality of what the labeling is good or not. I don't think n is equal to 50 out of 25,000 really makes difference here, but they just wanted to verify the quality of the human labels which are generated by the state-of-the-art model. So this is an example of how the model labeling looks like. This is the model, let's say this is the sentence, let's say, generated by Llama 3B, and you pass it to a web search, and then it identifies that, okay, Albert Einstein is important, let's label that as a span, was born on like unimportant text. They put a date here, which is correct, in Berlin. Okay, that's Berlin is false, and then they do a token level labeling. So we can think of it as a two level labeling. First level is like, okay, Albert Einstein is an important tokens. Y of I is equal to 1, and Y of S is equal to 0 because that's a true tokens. Second one is it's the same thing as it's important tokens, but it's true. And the third one is false. So that's an important token, but it's a false. It's a hallucination. Yeah, so that's how the labeling works. And the next part is how they attach probes. So here is a very basic rudimentary explanation how they attach probes. They took a llama model, so all the dashed boxes here are frozen, and they added an optional LoRA. So this is a hyperparameter they experimented with and without LoRA. I think LoRA helped them a little bit, but they also show that with just adding a probe on the final level is good enough. You don't need the LoRA, but if you add LoRA, it actually enhances your generation. Um, so here at this, this is one, let's say one decoding generation, you send a tokenizer embedding, go through n layers. And then for the nth layer, you take the hidden states, you pass it through a probe, and then this probe outputs a probability. That probability is 0 if it's not a hallucination, so 1 if it's a hallucination for that token, right? So that loop continues. So every token produced will have a hallucination. Right, check. Yes. So Ted is mentioning. Okay, there's a Swix questions saying, I think. Yeah. So the tokens. So the question here is that it's a confusion between entities and tokens. So they use for the web search, they extract entities and they take that entities and they label the tokens. No. So let's say here, the example here is here Albert Einstein is an entity, March 14th, 1874 is an entity, Berlin, Germany is an entity, and Claude will return Albert Einstein is equal to 0, March 4th, March 14th, 1879 as 0, and Berlin, Germany as 1. And so these are labeled this way, and they take that entities, aka spans, and then they label the tokens based on that. It's they use entities and spans interchangeably in the paper. A bit confusing. Yeah, so Eugene is saying that it's pretty cool that tokens are next to probes. Yes, that is actually pretty cool. So now you're not just generating tokens, but you're also generating the probabilities of the token. Essentially, it's a multi-level, which is kind of awesome.
So is the intent here that this model with the probe will be dual use for both answering the question, responding, as well as being able to return a hallucination probability as well?
Yes.
I see. So assuming that, let's say I'm using a LLM API, which I cannot fine tune to do this, I will not. Can I still pass the output that is streaming and pass it through, and still probe every token?
Yes, I tried that and it works.
Oh, okay. So that's really nice. So essentially, you don't really need a decoder. If you just purely want it as a hallucination classifier, you don't need a decoder head. You just use the probe head.
Yes.
Thank you. Very cool.
Yeah.
You tried this? Because I think in the paper they said that that's a limitation that they can't. They have a thing in the appendix where they show that it's not as effective to do it if you don't have access to the logits, or at least or not the logits, but the residual stream or whatever.
So what I did is okay, so here is what I did. So I entered some text, and during the prefill stage, so during the initial stage where it prefills, I identified that and I was able to calculate the probabilities. So essentially, I was not able to stream it, of course, but what I was able to do is like, okay, once the text is generated from, let's say, GPT-5, I was able to take that during the prefill stage, able to identify what tokens are hallucinations, right? So I don't need to decode it. Like I don't need to generate the next tokens after that. I just need to see, okay, which tokens are hallucinated. The why they
How
say
do
it's a
you
limitation
how do you
is
do that?
because
Is it essentially you just pretend like you start from the first token and you go through and you just scan
yeah
through it and get
yeah
very cool.
yeah. So the reason why they say it's a limitation is because you're not streaming, like you're not able to identify it during streaming, right? You
Yeah.
So that's a limitation.
So the
But
strong assumption here also is that this model, the model that you're using for hallucination detection, the data distribution of the text is approximately similar, which
yeah,
I guess in human text with enough training data, it should be approximately similar. Thank you.
yeah, true. Yeah. So if, for example, if you're saying, okay, it needs to be in the same level, right? So um, it needs to be in the same level as like Llama 8B should be in the same level as GPT-5, which is not true. Uh, so I would use this with caution. Another approach I was thinking is like take your training data, train this, and then use this as your like a final level check or something before you release it to the next step of your agentic pipeline, so that there's no hallucination on that pipeline. Yeah.
So I'm sorry, you lost me for a second. I don't know if this is what Eugene said or what you said, but I
Mhm.
thought I heard you say something about the probe is actually predicting the next token, and the probe's not
Mhm.
predicting the next token.
No. So that is true. The probes is not predicting the next token, but the probe sits next to the next token prediction.
So my understanding is the probe actually sits a little earlier. It's not
Yeah.
immediately before next token
So
prediction. I mean, you
yeah,
have
that
two
is true.
outputs.
Yeah, exactly. That is what I meant by sits next to that. So the like what I meant is that when you're predicting the next token, you're also predicting the probe. So outputs are two.
Yeah.
The place you place the where you place the probe in the code, they have made it modular. So you can say n is equal to, let's say, 31 or 29 or something, and then it'll go sit in the 29th decoder position, and then use that hidden states to predict the probe. Right.
Okay, right. Yeah. Because that's the whole point of this real time is that as the
Mhm.
token's coming out, you can actually interrupt generation if you are concerned about hallucination.
Yeah, that's exactly right. Um, yeah. Yeah. So yeah, that's actually pretty nice.
Adam, you had a
So
question and I saw you come out on camera. Did you want to ask it?
he did. Go ahead.
I don't know. I put some stuff in chat. I've
Oh, I'm
asked
sorry if I call you out.
like I'm happy for it to wait until we're further down the paper.
Okay, let's wait then. Thank you. Thank you.
Yeah. I see that LoRa here are like positive with changing the base model. Yeah, so they does correct me, Adam, if I'm not wrong. The idea here, like, are you asking like, hey, does LoRa change the way the model predicts a token? Yes, it does, and they have I will talk in the next part of the paper how they able to change that like how the model quality changes, like when you were training this hallucination check, because LoRa should technically change the way the next token is changing, predicting also.
I mean, my thought was to clarify with the LoRa question. Like the LoRas don't seem like they're part of the probe, the checking, the truthiness evaluation. There, my guess would be that the LoRas are purely once you have the ability to evaluate to make the results better for later generations, and hopefully I'm understanding that right.
Yeah, I've not done the abolition study removing and adding LoRa, so I just am believing what they mentioned. When I trained, I did train it using LoRa, and yeah. So I don't know what will happen if you just train the probe. So I don't know the quality will change or not. Yeah. So let me just jump to the next part of it. Like, hey, what does the loss look like? Because you have two things now. You have a probe and you have a regular generation. So what they have is a regularization term. Here they have this term. They set it to 0.1. Here, like, so majority of the loss is contributed from the probe, and some of them is through the regularization. So regular loss. So So yeah, so that is the loss. So let me jump deeper into the probe loss, because that is okay. So for the regular loss, they have two. Okay, by the way, loss regular. They have two types of loss regulars. One is a language model loss, which is essentially next token cross entropy, and the second one is a KL diversion between what the model without LoRA will predict and what the model with the LoRA will predict. Like essentially controlling the distribution between the changed model, the LoRA model, and the older model. So these are the two loss functions they experiment with, and they show the comparison in the results section. For the probe loss, is super interesting what they did, because you have a two-level classification. So you need to first identify which tokens are important and which tokens are entities or tokens are important. Um, um, then the second level is that if of the identified important tokens, it is true or not. So what they do is that they do annealing. First they start out with identifying the spans, which are like super important tokens, and then as the training keeps on continue, they change the weight to identify the hallucination. The first part of the loss is the span detection, and then the second part is the hallucination detection. And you can observe here, because the whole span has multiple tokens, right? Let me go back to my example here. Let's say Berlin, Germany. Let's say it's a 4 token. Again, this is an example here. It's a 4 token. All the 4 tokens need not be false. Technically, it's just only the Berlin is wrong or false. So only these two are false, right? So you cannot have a cross entropy loss for everything as a loss. So they do a soft cross entropy by putting a max term here, right? The idea here is that the max of all the probability predicted across the tokens should be 1, not every token. There needs to be 1. This surprisingly works. I was actually a bit surprised how this soft cross entropy is working. Yeah. So that is the one super important thing about this probability. I think the reason why this worked is because of this loss function, how they were able to switch between identifying which probe, like which tokens are important, and then switching to identifying, okay, those tokens are true or false. Yeah. So any questions on the loss specific definitions?
So what did P exactly represent?
The probability of that token. So the probe probability.
The probe probability. Okay, got it.
Yeah. So cool. So someone is asking, can it work with an API? So it should it should be able to. I don't see why not. Again, the base assumption here is that like you're training your own model, then only it can work in API. Yeah. I think Eugene answered that. Yeah. Yeah, there is another question. If you pre-train the hallucination classifier on existing hallucination training data, would it transfer to? That is a very Eugene asked a question, which so yes, that was super interesting to me as well. So the question was that, hey, if we use the existing data, can it generalize when we put a newly generated text? Yes, it works, because what I did is that when I was experimenting, I gave it all the data which they have generated, and I mixed that with like some chemistry questions for drug development, let's say, and it's able to identify like, okay, this protein structure is wrong, right? Which is pretty impressive. It's using its internal knowledge as well during this hallucination prediction.
Yeah, so I'm having a hard time understanding this here.
Mhm.
So Ted is saying that we need the internals of the models. So I'm thinking, is that like the hidden states or the residuals, or
Yeah,
what else?
so you need hidden states, right? So for the probes, you need the hidden states.
So we
For
don't
this,
exactly need the actual hidden state from the
mhm,
model that was used to generate it, right?
mhm,
We
mhm.
can
Yeah,
simulate it via this model.
exactly. Yes, that is what I meant by like you can take the outputs from GPT-5, then pass it to this model and identify which tokens are hallucinated.
So would that make sense, Ted? Adam?
So, so my TLDR here, okay, is that when you do this mechanistic interpretability research, people are saying the model actually knows that it's not confident in what it's saying, and if you just simply do the methods they talk about in the background section, where you look at the entropy or other things about the logits, you get a certain accuracy. You get 60, 70% or whatever. But what this paper is saying is that the model has internal knowledge of its uncertainty beyond what shows up in the logits. And that's why the linear probe can outperform just logit-based hallucination detection. So, and so the linear probe is actually looking for basically I'm going to say direction. If you don't know the mechanistic stuff, you might not know what I'm saying, but it's looking for a direction on the residual stream that says, I'm thinking about whatever I'm thinking about, chemistry, blah, 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 but I also have this thought. I'm not really sure what I'm saying here.
Oh.
Yeah.
So that's only available from the actual model that did the generation, and it's hard to just feed it into.
And the reason why you want around the 95th percent layer is because the last few layers are about refining next token prediction. They're not actually about thought understanding creation. And so around the last 5%, you actually tend to lose thought information because you're stripping it from the residual stream so that the residual stream is just next token information and nothing else. So you would get worse linear probe information if you did it after the last layer instead of at the 95th percent-ish layer.
That is true. That is true.
That makes sense?
Yeah.
But I think it bears repeating that the experiment that you did was that you actually used a different model or potentially a different model, right? So you like you take GPT-5's output, run it through Llama, and then use its concept of is this a hallucination or not, and that was also reasonably effective.
You mean Llama, right?
Yeah, Llama.
Yeah, and that was also effective, right? In Berkeley.
Yes.
Seemed to work.
Yeah, seemed to work, but like a key is that that information was general enough for that both GPT-5 and Llama knew about it, right? So if Llama doesn't know, then it doesn't work.
Okay.
So
yeah, it would be
that
interesting. So did you calculate any loss curves or anything on that? I mean, not loss curves, like a ROC curve or anything.
No. It was just a simple test, which I did, like, with like, let's say 10 or 15 examples. I didn't go more than that. Yeah.
Okay. Yeah.
I just wanted to see if it actually works before I,
Interesting.
that's not skill. Study on that.
Sorry, guys, just to clarify, you took GPT-5's output and you calculated the probability of hallucination based on what it was trained for. So it's basically guessing based on what it was trained on from an open source model. And if there is an overlap between the data sets, then it probably works.
Yeah.
Otherwise, it doesn't, right?
Yes.
So it's not exactly reverse engineering, it's just a guesswork. I mean,
yes, it's a guesswork.
Okay.
It's a guesswork. But where it changes is if you have, let's say, domain-specific information. You can make the super, Llama 8B model as your domain expert, and then pass that through. That'll be very powerful, right? So let's say you have some proprietary information or some confidential information for your own stuff, and now you have GPT generating this stuff, and you can identify, oh, this is a hallucination according to my knowledge. GPT might fight and may not know or something. So we can mix and match.
It's using a smaller model to detect some very specific, I won't call them hallucinations anymore. It's just that factual errors. And that's something you can detect because you have a smaller model trained on it. It could be even faster.
Yep.
Similar principle to speculative decoding in a sense, not using probabilities, but yeah.
Yeah, I would say Spectec is a bit different. But but I totally agree. There is a similarity between these two.
Okay.
And I think you could go either way. Your hallucination detection model could theoretically be larger, but of course, then it'd be expensive. So you're probably not going to do it that way. The authors of the paper would probably hope that if this technique were refined and made better and actually useful, that then GPT-5 would just support it, and you wouldn't have to have your own standalone llama that you run, side by side. But it's an interesting thing. Basically, when you pass any text into this llama model, whether it comes from GPT-5 or if you just write it yourself, what llama is answering is, if I had generated this text, would I have been confident or would I have been uncertain and maybe hallucinating? And so to the extent that llama is right, then you can use it as a hallucination detection for your 5-year-old kid, or you can use it for GPT-5 or for whatever you want.
Yep, that's true. Cool. Yeah, so that's a very good, yeah. So the comparisons, what they did. Let me just jump to the next part of the paper. The comparisons, they did entropy, so which is like and perplexity. These two are like models internal representation, like how surprised it is by generated token. The second one is the semantic entropy. I think Ted already explained this a bit, where you just sample multiple times and then like essentially decode the same token multiple times and then group it and see, okay, what is the direction of this group, and like if all the direction is the same, that means that, okay, probably not a hallucination. If it is like direction is like larger, so and that means that your aggregated direction might not be same for all the generated tokens, that means it might be a hallucination. That is a comparison. That was a state of the art actually. And the black box self-evaluation. So this is essentially a judge, LLM as a judge approach. Yeah, so the experimental setup here, they have a Llama 8B and 70B model. The repository also has ability to use any Hugging Face model, which is kind of cool. But they also tested it out for like JAMA models as well, which works. You can see here this probe. So just your perplexity, like not doing anything and just pasting things on a perplexity, like Ted mentioned, works well. Like 76 area under the curve is like 0.76. But if you use like this probes, even a linear or a llama probe, LoRA probe. Let me clarify what is a linear probe is. The linear probe is there is no LoRa, right? So it's just a probe, that's it. LoRa is an optional. So, but when you add LoRa, it just is essentially is very good in identifying this. Both recall and area under the curve is actually pretty high. So this is a summary of the result. And they go like, and they release the data set as well, which has about 25,000 total samples. Yeah, so evaluations, I'll skip all this. And so this is the out of distribution performance. So this is the like what I was mentioning, like what if the training data is not present, what like, if the concept is not present in the training data, and if you in your fine-tuning data, it is present in the pre-training data, it still performs well, which means that it's using its internal hidden states pretty well. Yeah. Yeah, another one. Okay, this is actually pretty. I still don't know why this happens. I was a bit surprised on this as well. So if you train on samples which have only short form text, it doesn't perform well on the long form. And long form text. If you have hallucinations identified on long form text, it doesn't really perform well on the short form text. I don't know why. I don't know why it is different, because I genuinely don't know. Like I couldn't understand like this part of the paper, because it theoretically it should not matter, but apparently it does. So if anybody has any insight on that, I'm happy to hear and like ask questions. But for me, this part was very surprising, because I would assume how does the length of the text matter for your hallucination detection of the one token? Apparently it does, right? So I was not sure.
Yeah, I thought that was really maybe even the most interesting part in the paper, because I mean, my explanation for that was that it's actually looking at the context around it and saying, oh, this is a likely thing to be hallucinated, right?
Yeah, but That
And
is
so
if that is true, then
Yeah.
long context should always beat the short context, right?
Well, maybe maybe I would say that supports this exactly what we see here, because in the short form test, then maybe that model like relies more on like wider context, whereas the short form one more relies on fact or something like that.
Why is this
That's
result unintuitive to you, Prakash?
Yeah, so because think of it, right? So they say a short form text is, let's say, a one answer, one question, right? So they use like let's say 100 token or 200 token answer, and they mark some tokens as hallucination, and they train on that. That's it. The long form is essentially like an essay of 600 or like let's say 10,000. And here they mention 8,000 tokens or something like that, and they mark hallucinations. And they take two models which are trained, short and long, and they apply it on other data sets. Which is and it does not perform the same way. So for me, how does the length of the text matter? So yeah, that is why it was. Ted, I have a question. You have and
So I think my intuition around this result is that it's not about that the model is any different. It's about whether or not we trained a good linear probe. And so what they're saying is that the signal in short is, because it's short, it's not getting a super accurate signal. And so then the probe just doesn't learn very well. I don't think it's about whether or not hallucination looks different, which is why if you get a really accurate signal by training on long, it works pretty well on short because it's the same hallucination signal. So it's really just a matter of what kind of training data you need to get this probe well trained, is the way I read section 5.
Okay. Yeah, that makes sense. So it's essentially, it's not the yeah, I wouldn't change the plot as like performance on good quality data versus performance on bad quality data or something like that. Yeah, okay, that makes sense. Makes a little bit sense. Yeah, so here is the cross-model generalization, which was super interesting. So here you can think of it as a text generated by one model, but the probe is another model. Right. So let's say they generate the Quen 2.57b text, and they validate it or probe it on 70b model, and it works. Right. So here is an indication of why one model text works on another model, and why GPT-5 works when I tested it out with the Llama model. Right. So and so another surprising thing is, if you have um, a dumb model, which is, let's say, is 2.57b, which is maybe a dumb model, and then you have a probe model which is bigger, 70b model, it performs actually better. Which is which is actually kind of interesting, and it intuitively makes sense also. Because you have the 70b model is a very intelligent model, and it can identify hallucinations well because it's internal thought well. Yeah. So any questions on this aspect of the cross-model generalization? Okay, so I'll continue. 12 more minutes. So yeah, so here is the LoRA. So I think I missed a thing here. Yeah, so this is an explanation, and the next part is they hypothesize that, like, hey, if this model, if we add a LoRA, is the tokens produced different than if we don't add LoRA? I mean, it has to be different, right? Because the LoRA contributes to token decoding as well as probe. So it has to be different. And what they do is that they play around with the regularization term. So during the in the loss regularization term, just to give a context. So let me jump to the loss regularization term here. So here there's a probe loss and then the regularization. And then this is they play around with this the lambda term here, and then they increase and decrease and see how the model performs. The MMLU and essentially the model strength. And what they see here is that it does affect, but there is a sweet spot here with KL divergence at 0.5, where it doesn't deviate too much from the original model original model's decoding, but still is able to perform well in the hallucination detection. So very interesting results. So I have last 10 minutes, so let me just jump through the next one. The next one is pretty interesting. So this result here. So in streaming, let's say you are generating tokens, right? Say first token, second token, third token, fourth token, and then fifth token, you realize that, oh, it's a hallucination. What if you stop generating the token and say, I don't know, right? So you can do that because you are going through you have a probability of hallucination for every token when you're using this model to generate tokens. So that's what they did, and they were able to say that if you do that, if you have a threshold of let's say 0.5, and you can essentially increase the model performance because you can say I don't know, right? You can refuse to answer what you actually don't know, which is which is a skill which is currently lacking by current LLMs. They just, even though they know it's wrong, they keep generating. But you can introduce the skill where as soon as the model realizes it doesn't know, it can stop. So this is one skill addition you can do to the models in addition to hallucination to say, I don't know. Super useful. It doesn't let, yeah. So any thoughts on this? I thought this was actually super good, super good result.
If could you explain? I don't think I understand this graph properly because
Yeah.
I don't understand why you could have an attempt rate at less than 1 if you have no monitoring, right? So that like that rightmost point, I don't understand that.
Yeah. So let's say you have a super aggressive monitoring, right? So let's say t is equal to 0.1, right? So you have the token number 1, the probability is 0.01. The token number 2, the probability is 0.1. You stop at token number 2. You don't generate more tokens. Right. So that
understood. Yeah. But I mean, so there like t equals 1, like the rightmost point, that's no monitoring. So you never are.
Yeah.
But then why is the attempt rate then 0.8?
But because it's still, there are some answers it doesn't respond. Like it is
Oh,
not.
it'll still say I don't know to some things just because it doesn't know and it recognizes that. Got it. Okay.
Yeah. Yeah, I mean, at least that is my understanding of how they did this. So
yeah, that makes sense. Thank you.
Yeah. Yeah. This will be super good if someone like Claude or something did this, like saying I don't know, it'd be super impressive. At least for our agentic pipelines. Yeah. So other than that, they say limitations. Uh, the limitations of this paper, they say, okay, then you need a lot of text to the entity level hallucinations are problematic because it doesn't have the context of the whole thought process, etc. But I think that is okay. That is the best we have. So the limitations here are not as concrete or as detailed. Yeah, so I think that is it. They have some discussions here, but those are really not that doesn't really add anything to the paper, I would say. Yeah. So and the appendix is they just explain some what the data set looks like. They also give prompts and how they generate a text. They go on to explain how the baselines look like. They give prompt for all the evaluations like LLM judge and everything, and say they have some also additional results, which is actually kind of good. Yeah. So that is all the things here, and they have some results here, which compare across. They just, what if you just fine tune models and black box evaluation? Cool. So I think that is about it. Any final questions or anything that you guys want to bring it up?
Maybe a general question, like this was really a sort of token level. So if you had a model which just gets asked something that's where the sort of answer is really quite a lot of tokens, like you need 10 plus tokens, can this somehow be expanded to these kind of cases, or do you then really have to think of different hallucination detection methods?
So you mean like, let's say a group of like 10 tokens, you want to identify if that is wrong, right? Yeah, that's not
like, yeah.
That won't work because this is done at token prediction level. So it's like one token at a time. So it won't work for a group of 10 tokens. That's actually a very good limitation of this paper.
Thought the section 6 limitation was kind of interesting, where a lot of this relies on the backbone of verifying the facts with Sonnet 4 and search, right? And even with that, there's only like 80% recall and 16% false positive. So even with generated text and then having Sonnet 4 and web try to verify facts, still has quite a bit of false positives. So like it's a bit of proof of concept work, right? Like they didn't really do that much in terms of like more strict guardrails on ensuring facts are there. So just a word of caution for people that do actually try to use something like this. You can probably get those numbers to be better with better guardrails, right? Just have more rounds of filtration. So like off the shelf, that's a bit worrying that the code allows in 20% false issues, but you can always do better if you try.
Yeah, that's actually true. And that is the reason why I was mentioning like, hey, injecting hallucination is better than, let the model generate and then we'll do web search and check if that it's hallucinated or not. Because, injecting hallucination, you can control how much hallucination was injected. Whereas here, you cannot really, you don't know.
I
You don't know
agree,
what you don't know.
and I think that's especially true given the results that they were showing, that like the cross-model generalization, that sort of they even mentioned this kind of suggests that it's because like intrinsically there's information in the text, so that you should, maybe the concern about being out of distribution is not such a big concern, and is maybe I would have a lot of concern, and thank you for bringing up Vibu, because I did have concern about this, and that if you only have 80% recall on your or especially your false positives, or either way, if then in your training set, then you're not really even, how do you even, and your validation set, then how do you even know that you're like all you know is that I'm like sort of I'm able to kind of get to where I was with Sonnet 3, and not, you don't really know how you perform in the real world.
Yeah, that's true.
And I think while we're at it, you might as well highlight the third limitation since it draws on that. All this paper is about entity hallucination, right? So like facts, names, stuff like that. But if you're going deeper, it's not trying to check for hallucination and reasoning, right? Or like contextual stuff like that. So like someone in here mentioned using this for RAG. Ankit brought it up, using it for RAG context. This is all only trained on entities, right? So it's checking stuff like, is this date correct? Is this correct? But it's not necessarily going to work on, stuff like reasoning, stuff like, is this the correct context? That's another limitation. And then when it comes to how you train it, you can generate stuff with RAG, but then this verification step doesn't really, you have to do more work there.
Yeah, that is true. So I would be I would be interested in, like, can you ground? Do you even ground? Do you even need to ground thinking? I think maybe do not ground thinking and only ground the generation part of it, or something like that, because
I think there's aspects to both, right? Like if you think in the ed tech space per se, like you have a copilot that's teaching you something, there's value in the reasoning steps, right? You want valid reasoning. You don't want hallucinations there. If you're trying to learn, you often care more about process than end output. So
Yeah.
It's always useful. And it's not like it's like non-trivial to verify this stuff. It's just a different objective that this isn't trained on. Like you can check if stuff is a proper reasoning path. It's just not what this repo does. So it's just something to think about. And
Yeah.
like Ted mentioned, this is, I think, part of the maths work, right?
Yeah.
It's like
Yes.
a internship that's in the
Yeah.
interp safety space.
Yes, I think, yeah. So I think there was an internship product because like the only one author is from Ideation. Yeah, I don't know where though. So because Neil Nanda is from Google. Yeah.
Yeah, he's the big maths advisor.
Mhm.
A lot of the maths papers just started coming out. John Schulman was advising one, so technically another interp thinking machine paper, but you know, it's all maths internship work. But this is some of the cooler stuff.
Yeah, definitely. Awesome. Adam, you have a hand up.
Yeah, if I can kind of follow on with the sort of thing that Viva was saying at the start. Sorry if I butchered your name. The, yeah, like I put a question in like way earlier on that was it seems like they're sort of when they do the entity checking, they're checking does this date, this name, this whatever exist mostly, or like it maybe exist with some like similar context, but
Mhm.
it jumped out to me that like that it's good to check that the name is real or whatnot, but like it seems like you could like the model could score well using like John Smith for every name. You know what I mean? Like it's suggests that there's a way for it to be orthogonal to truth. You know, uh,
That is true.
and I
That's
imagine
true.
there's something more in the paper that kind of talks about that. I didn't read this prior to arriving, but like I just wanted to question something in that space, I suppose.
I think the paper
Yeah.
goes over it actually. They talk about Claude for web search, so breaking it down to token like minimal text span, and then they search the web and give it 3 labels: supported, non-supported, or insufficient information. Like they had a whole section on it, and then they give it a
Yeah.
binary classification. So like it's in
Yeah,
Yes.
there.
if you go to Appendix C3,
Yes.
this is the
Yes.
prompt that Sonic got to say verify this fact. So it's not just does Berlin exist, it's
Yeah.
actually verifying
Yeah.
like was Einstein born in Berlin.
Yes. That is
And it
exactly
does web search. So it's not
yes.
even just based on Sonnet. It's somewhat more grounded there, right?
Yeah, it is. It's a bit more grounded there. It doesn't like it doesn't really just use the information as well. But the problem comes in when you're deviating from this data set, right? So that is where I don't know how well it works. So
Yeah.
and it works kind of, but yeah.
And in terms of like basic improvements from internship project to production, like even stuff like this, right? So like the guardrails that aren't caught, and let's say you wanted to make this verified for reasoning or other stuff, this is still
Mhm.
doing 3 things in one call, right? Like this is
Mhm.
one call that's doing text spanning and
Yeah,
search and labeling. Like the
yeah,
simplest solution, break those into 3, right?
yeah,
You're giving 3 very distinct tasks to one LLM call.
yeah.
Sure, it
Mhm.
can probably do it, but
Yeah.
you could probably do better.
Yeah, exactly. So like, first call, make it and verify it's true. And then second call, like, hey, which part of it's not true? And then third part, like which part in the text is actually not true or something like that. We can break it into 3 calls and have a better, I think false positives and like your precision will also improve like drastically if you do that. Yeah, I do agree.
Yeah, and if you have real data instead of synthetic stuff, you can do more of this in parallel. You can bring back data, you can augment it. So there's all you can do, but I think it works as a good proof of concept.
Yes. And yeah, it's actually super cool that they open the repo. You can experiment with that a lot. Like it's a very let's say very good quality repo.
It's like splitting into 3 thing. Like this seems like sort of what Peter was asking about earlier. Like you could attach that to whatever you wanted to.
Yes, that is true. But like, but the Peter is like he wants to predict if this set of 10 tokens are true or not. But you cannot really do that. Yeah, you cannot really do that. Here, the label is per token. Does that make sense?
It wouldn't stop you from either running the 10 token passage through either classifier or the Claude prompt here or whatever else for further evaluation. Like it's not the same, but like
Yeah, I mean, in the paper, they
it's
basically
not
just say
doable.
if you take the max of the token level predictions, that's a reasonable first whatever proxy for the 10 token prediction.
Yep. So, there are no other questions. We'll stop sharing and yeah. So guys. I think I'll end the call.